So let's do an independent samples t-test in SPSS. We will be using puppytraining.sav for our dataset. We will use this same dataset later when we do a paired samples t-test. Here is the setup for our research. There are two popular ways to train dogs. One involves using a clicker, which creates a sharp click that reinforces when the dog has done something right. The other method, of course, is food training, or treats, in which the dog gets a small morsel when he responds correctly. Because this is an independent samples t-test, the researcher is going to use different dogs in each group. Mickey is a dog trainer studying reinforcement effectiveness. He randomly assigns 16 puppies to 2 different reinforcement training techniques. After training the puppies, he measures the number of correct responses by each puppy in 10 exercises. Was there a difference between the 2 training techniques? Let's walk through the 5 steps of hypothesis testing. Step number 1, select the appropriate statistic. We will compare 2 independent samples. One sample is the puppies who were trained using clicker training. The second sample was the puppies who were trained using food reward. To compare these 2 independent samples, we will use the independent samples t-test. Step 2, state the null and alternative hypothesis. We want to know if the means of the 2 samples of puppies are different. We are not saying which group will be better, so this is a non-directional, two-tailed test. If we said that one group would be better, that would be a one-tailed or directional test. Because this is a two-tailed test, our null hypothesis will be H sub 0, mu1 equals mu2. And that means that our alternative hypothesis will be H sub 1, mu1 does not equal mu2. Step 3, select a level of significance. Now we have already established that this is a two-tailed test. Our alpha level is going to be 0.05. The degrees of freedom for an independent samples t-test is n1 minus 1 plus n2 minus 1, or n1 plus n2 minus 2. The total sample size of both groups minus 2. Group 1 has 8 puppies, Group 2 has 8 puppies, so together 16 puppies minus 2, the degrees of freedom are 14. And remember too that in a test like this, I'm simplifying, so we really ought to have 30 or more in each group. But for this case, so that we could do it by hand, I've created groups that are smaller. To find the critical value, we will go to our students' t-distribution table. For an alpha of 0.05 on a two-tailed test with 14 degrees of freedom, our critical value is positive or negative 2.145. Alternatively, you can download the RStats effect size calculator for t-tests and use it to determine your critical value. Here you can see the 6 things that you can do with this effect size calculator spreadsheet. Click on the green tab for critical values. In the upper left, we have our typical setup for an alpha equals 0.05 two-tailed test. Simply enter your degrees of freedom, 14, click or hit return, and your critical value, 2.145, appears right here. But wait, there's more. If you are not doing the typical two-tailed alpha of 0.05 test, enter your degrees of freedom here. Click, and you'll get critical values for both one- and two-tailed tests at a variety of alpha levels. You would use this box if you were doing a t-test by hand. So any t-values exceeding positive or negative 2.145 indicate that the sample of puppies being trained with clicker training was statistically significantly different than the puppies being trained with food reward training. Step 4. Calculate the statistics. Let's go to SPSS. Using the dataset, puppytraining.sav, we begin in variable view. I want you to see that I have done something with this data set that you should never do. In fact, click over to Data View. I have included data for both an independent samples t-test and a paired samples t-test in the same data set. Never do this. I have only done this to illustrate something about the t-tests, which I will show you a little later. When you do research, you should set up your data appropriately to the test that you will actually do. Let's go back to variable view. The first of the two variables that we will use is correct, which has 0 decimals and is at the scale level. The second variable is group, which also has 0 decimals and is at the nominal level, indicating that it defines the two groups. Now we need to assure that we know which group is which. Click on Values for group. The value of 1 has been assigned to clicker training. The value of 2 indicates food reward. So now we are ready to do our analysis. Click on Analyze, Compare Means, Independent Samples t-test. Move the scale variable correct into the test variables window. Now place the variable groups into grouping variable. You see the two question marks? That means that SPSS is asking for how to code each group. Now you may wonder why SPSS is asking you for these groups because you only have 2 groups. But imagine if you had some educational data and you wanted to compare scores from freshmen to scores from seniors. You might want to compare group 1 to group 4. So we need to define our groups. Click on Define Groups. Group 1 will be 1, group 2, 2. Click Continue, and we see that SPSS now knows which groups to compare. Click OK. In the output window, we see the group statistics. We can see the sample size, the means and standard deviations for each group, and the standard error of the mean. We will use these for the APA write-up. This next box gives us the results for the independent samples test. The first thing we need to establish is that the assumptions of the test have been met. One assumption of the independent samples t-test is that the 2 samples have approximately equal variances, and we will test this assumption using Levene's test for equality of variances. Remember that Levene's is testing whether variances are equal. That is the null hypothesis. No difference between these 2 variances. So we do not want them to be statistically significantly different. We do not want Levene's test to be less than 0.05. We can see that Levene's f-value is 0.503, and the probability associated with that f-value is 0.49. Using the analogy of $1, this significance value is 49 cents, and that is not less than a nickel, 0.05. So is Levene's test statistically significant, p less than 0.05, or not? This Levene's test is not significant. Therefore, the variances are not statistically significantly different. Therefore, the variances can be assumed to be equal, or close enough to equal. We will then interpret off of this top line where it says equal variances assumed. So how can we interpret these findings? First, the t-value of 1.587 does not exceed the critical value of 2.145. Degrees of freedom is 14. We can see that the significance value for the t-test is 0.135, which is greater than 0.05. We also see that the 95% confidence interval for the difference between sample means, which is mean 1 minus mean 2, shows a lower bound of a negative 0.44 and an upper bound of a positive 294. Because this confidence interval crosses 0, it includes the null hypothesis value of 0 difference. All three of these findings tell us the same thing. The means of these two training groups do not differ statistically significantly. Let's go back to our 5 steps of hypothesis testing. Step 4, calculate the statistics. The t-test value is 1.587, and we will round that up to 1.59. The critical value was 2.145, so the obtained t-value does not exceed the critical value. That means that the test is not significant and the two groups do not differ. Step 5, make the decision. The clicker training group was not significantly different than the food reward training group. Our t with 14 degrees of freedom equals 1.59, p equals 1.35. This is a non-significant test. We have failed to reject the null hypothesis. To calculate Cohen's d effect size, we will use the RStats effect size calculator for t-tests. We are calculating a Cohen's d for independent samples t-tests. So click on the light blue tab for effect size between. You have 3 options here. Option 1 is for when you have the group descriptive statistics. So enter the sample mean, 6.38, the standard deviation, 1.408, and the sample size for the first group, 8. Then the sample mean, 5.13, the standard deviation, 1.727, and the sample size for the second group, also 8. Click, and the Cohen's d is 0.793. According to Cohen's conventions, this is on the borderline of being a large effect size. In fact, I think we can call it large. The reference for Cohen's d effect size and its interpretation, Glass's delta, Hedges g, and the formulas that I used are below the table. The second option works well when you have findings from a journal article. If the authors reported a t of 1.585 with 14 degrees of freedom, you would enter the sample size 16, which is degrees of freedom plus 2, and get the Cohen's d, or Hedges g, if you were doing a meta-analysis. Now, this third option requires output from SPSS. To get the measures of effect size using this option, you should go to the SPSS output window. Double-click on the Group Statistics box to activate it. Here we need the same sample size, mean, and standard deviation, except we do not need to enter them ourselves. Highlight, copy, then flip back to the RStats effect size calculator for t-tests. Paste the output, and click. The Cohen's d calculations are exactly the same. You can also see that we have an R-squared effect size. This is how you would write up these results in APA style. An independent samples t-test was conducted to determine whether puppies trained with clickers performed differently on exercises than dogs trained with traditional food reward training. The groups did not differ significantly. The mean for the clicker training group was not significantly different than the food reward training group. These findings do not support the idea that clicker training is more effective than food reward training. This last statement about the meaning of your findings would go in your discussion section if you were writing this up for a paper. Finally, if you look at the data for these 2 kinds of t-tests, you will notice something remarkable. The data are exactly the same. The group means are exactly the same in both tests, and yet the independent samples t-test that we just did was non-significant. But you will see in the next video that the paired samples t-test with exactly the same numbers will be significant. This illustrates that an independent samples t-test is less powerful than a repeated measures t-test. This means that you are less likely to find a statistically significant difference between groups using independent samples. It doesn't mean there's anything wrong, but only that you should consider the power of your test when you do your research design.